Hello again. Good afternoon. Thank you for being here in the last presentation of the last day, the last session, the last whatever. My name is Gustavo. I am a professor at the Federal University of Pará here in Brazil. And this is a joint work with my former advisor, Fernando Castor, and Gilson Rocha, who was a student of mine. So the name of the paper is Comprehending Energy Behaviors of Java IO APIs. And you may know better than me that this is a real issue on your smartphones, on your laptops, on your smart watch, on your smart whatever. And you, as a user, you may what? So you as a user, you may know better than me that you have the choice to choose the device that you want to have because that device will may have more battery than the other device, as well as the app, as the software that runs on that device that will make that device last for longer than the other apps. So you have the power to decide what you want to buy, what you want to use in terms of apps and software. But essentially, this kind of concern is not only here in academic conference. We can also see people discussing that even though they do like the app, in this case is the Waze app, I do like this app is consuming such much energy, my battery is going to die very fast, what the hell? So in that sense, what we can do in terms of developers is that we have no other choice instead of going to the software, to the app, in a way that try to make that more energy efficient. But how can we as developers do that? Because we are creating software that are complex and big and whatever. And how can we start? How can we find the place? How can we see the opportunity for making the software more energy efficient? This is a good question because it's very hard to start. We are still looking for intuitions or for tools or for methodologies that can help us to identify the places or the spots that are more energy consuming than others. But in this talk, I would like to talk about I/O stuff that may matter in terms of energy consumption. And for those that don't know, if you may need to do any kind of communication in your software, you have to use I/O. If you need to communicate with the database, you have to use I/O. If you need to communicate with the internet, you have to use I/O. If you need to communicate with other device or IoT or whatever, you have to use I/O. So I/O is a very common programming concept that developers use on a daily basis. And if you are a Java developer, you may have four groups of classes that help you to do I/O. And if you take a closer look at one of these classes, we did a carry of classes that are related to this class here, and we saw that there are at least 100,000 projects on GitHub that use these classes here. So these classes are important, and people, developers, they use that class frequently. So another closer look at this class, there is a very interesting thing here, because you don't need to read this code, but you need to just focus on this part here, which we are instantiating the object. This other part here is just boilerplate code that you need just to do the operation. But if you take that away for a moment and just look at the instantiation, I can change that class to another class, and that would work again without having to change any line here. And then I can do that again and again, and eventually I would have some classes that I just need to understand the design that they are using, the way that I can create, instantiate these objects, because they have very similar design choices. And we also can see that these classes are heavily used, as I told you some slides ago. But the question is, these classes are used, these classes are very similar, but how about their energy usage? So how about the energy consumption? And the point of this work is to understand, first, what is this landscape of energy consumption of these Java I/O classes? And two, Since these classes they are very similar in terms of design choices, can we change one class to another in a way that we can improve energy consumption? So these were the questions of this work. And to answer these questions, we did an experiment in which we have a very commodity software here, Intel CPU with 4 cores, and another Intel CPU with 40 cores, in which we did many manual experimentations, and we use this library here to get the energy consumption of these environments. I don't have the time to talk about the details now, but if you have more questions, I would be happy to answer about how can we measure energy consumption. But then after that, we went to the Java development kit, and we found that there are many classes that do this kind of I/O stuff, like I told you in the beginning. And we selected for this study 22 classes. And we also, after selecting these classes, we did some benchmarks over all these classes, and we grouped these benchmarks in terms of the micro benchmarks, the optimized benchmarks, and the macro benchmarks. I will explain to you a little bit better very soon. So for the micro benchmarks, what are these kind of benchmarks? Are very small, naive, that only exist to expose the behavior of these classes in terms of energy consumption. So here I have a benchmark that has 5 lines of code, maybe 10 lines of code, not more than this. And in this case, we are doing just a very naive reading operation. So you do that for other kind of classes. In this case, we do the same for writing operations. And this is the micro benchmarks, just to do the very basic thing. For the optimized benchmarks, it's a different theory, because in this case, we use this website here, the benchmarks game, where very experienced developers, they go there and submit one very optimized source code for a given problem, and they do many kinds of benchmarks at this website. So we took advantage of this database and we used 3 benchmarks that are available there. The first one was this FASTA benchmark, and a little bit bigger than the other ones. It has 300 lines of code, and what it does, it basically creates a DNA sequence. And for those that don't remember, DNA is a sequence of A, T, G, and C letters. So basically it does this. The other benchmark is this K-nucleotide, which take as input the output of the other benchmark, and then it's processed to understand, to see the number of A letters, T letters, and more complex patterns such as CC, CT, and GGT, and whatever. So this is the other benchmark. And the third one is this reverse complement, which also takes the input, the output of the other benchmark, and creates another kind of DNA, but in this case it is the reverse complement of the DNA, which in our case would be something like a reverse engineering of the DNA. So these are the optimized benchmarks that we use it. But as I told you, we also have these macro benchmarks here, which are very stable and very old and very used and very known benchmarks, such as Zela, which is a library that transforms HTML files into XML files, and this PG-JDBC driver, which is the official driver of the Postgre database, and many others. Just to give you some numbers, in this Xenon framework here, it has something like 100,000 lines of code, so very big and using many instances of the class that we are studying. And for these macro benchmarks, we also did some studies, so we varied the input size from a small number of files up to some hundreds and thousands number of files. So we did all this configuration in that 2 machines that I told you some time ago. So what we found? Basically, we found that these 2 figures here, that I try my best to explain to you. In this figure here in the right, you can see that are the results for the APIs that do reading input operations, and this figure here on the left is the benchmarks that do output operation, writing operation. And then the most interesting thing that I can see so far is that reading operations consume at least 3 times more than writing operation, as you can see by the side of the bars here. Other interesting thing to see is that there are some patterns in terms of energy consumption. So here I have 3 classes that have basically the same amount of energy usage. And if you take a look at this other side of the same picture, you can see that these other classes here, they have a very similar also amount of energy. But in this case, it's a very good one. So we are still understanding why that's the case, but in this case here, these classes, they came from Java 1 more than 25 years ago. And in this case here is classes that were introduced, I think, at Java 6 or 7, so they are more optimized than the other classes. Also, it is interesting to see that this class here is the class named Scanner, which is the most popular class that we found when carrying the GitHub. And the energy consumption of this class is a little bit big, which means that a lot of people are using a class that's not very good in terms of energy consumption. So this was the findings for the first research question. And for the second one, what we did was to, we asked whether we could refactor from one class to another. So we have this procedure here where we identify the instance of the Java classes, and we try to refactor this instance based on the pattern of the classes, and we naively try to compile and run again. So that was the procedure. Obviously, there are some threats here, and then we can discuss there, and then we can benchmark again these classes. And after this process, we did 22 manual refactoring transformations. And these are the findings of this study. I know that this table is very hard to read, but again, I'll try my best to explain to you. Here in blue, we have the results for the optimizing benchmarks, the one that we didn't wrote, that we took from that website. And these one here are the results from the macro benchmarks, the one that are big and stable. The red cells here are the cells that we were not able to change, that we did not refactor. And the green cells are the default implementation, that makes no sense to change. So now, the green cells are the cells that we, after doing the transformation, we were able to reduce the amount of energy usage. So we were able to reduce, in this case here, the K included benchmark. Using this implementation here, files read all lines, we were able to reduce about 1% the energy consumption. But in this case here, using the Xenon benchmark, changing to this buffer input stream implementation, we were able to reduce about 17%. However, there are also some issues here because we also made implementations that were bad in terms of energy consumption. So in this particular case here, the PGJBC guy, the transformation that we made decreases the energy consumption in 100%. So the answer for this question is, can we improve the energy consumption? Yes, we can improve, but you should take care because you can also increase the energy consumption. We also did some experiments varying the workload, and what this figure is trying to show to you is that for every kind of workload, every group of bar here, the results are more or less the same. More or less in the sense of the one that is the best in one experiment is also the best in the other experiments. That says that our transformations are more or less stable in terms of varying the number of input size. And yeah, changing the input size will not change much the overall results. And yeah, that's it. I'm about to close the talk. And in this talk, we saw that there are some groups of classes that do I/O in the Java programming language, and we studied 22 of these classes, and we observed that there are some classes that obviously consumes more energy than other classes. In particular, the newer version of the Java classes brings some classes that are more energy efficient than others. And we also noticed that we were able to reduce energy consumption in some cases, but in others we will see some very, very bad things. So then I'm more than happy to take your questions. Thank you.